Hello everyone, welcome to a new lecture of our course on processing in memory systems. Today we are going to talk about another real-world processing in memory architecture, Alibaba hybrid bonding PNM engine. Remember that we started this series of lectures about real processing in memory architectures with HB-PNM. HB-PNM is based on DDR4 DIMMs, and inside each PIM chip there are 8 memory banks called MRAM, 8 DRAM banks called MRAM, and 8 DRAM processing units or DPUs, which are these small processors, each of which are near the DRAM bank. The second proposal that we presented here was HB-PNM or SIMDRAM from Samsung. In this case, one PIM unit, a SIMD-PIM unit, is placed in between two banks. It's based on HBM2 memory. The next one was from SK Hynix. It's called Accelerator in Memory or AIM, and it's based on GDDR6 memory. In this case, it's also a SIMD unit, an array of 16 multipliers, and after that, another 3 to perform the reduction. Each of these units is placed near each of the banks, the memory banks. And the next design was AX-DIMM, also from Samsung. In this case, it's a DIMM-based solution with 2 memory ranks and an FPGA on top of the DIMM. And this FPGA can be programmed for different purposes. In the previous lecture, we discussed one use case for recommendation systems and another one for databases. Today, we talk about this Alibaba 3D logic to DRAM hybrid bonding with processing near memory engine. It was presented last year at ISSCC. And the motivation, as usual, is the data movement bottleneck, in this case for machine learning workloads. As you can see on the slide, the requirements of the AI models and the machine learning workloads have increased by 750 times every 2 years, while the hardware computation capability and the memory system capability increase only by 3.1 and 1.4 times respectively. And this affects many workloads, including machine learning workloads such as natural language processing, recommendation systems, graph neural networks, or multitask online inference. In this work, Alibaba engineers focus on recommendation systems. We will talk about their architecture, but before that, I want to go over one processing in memory classification that they have in their paper, and I find it pretty interesting. As you can see on the slide, these pictures are distinguishing memory process in gray of logic process in cyan. And as you can see, there are traditional architectures. This is what we in this course call processor-centric systems, such as CPUs, GPUs, or FPGAs, where we typically have memory and compute units in separate chips connected by an off-chip link. There are also more tightly integrated proposals or devices where, such as what it's called 2.5D PNM, where memory and computation are connected through a silicon interposer. This is the case of GPUs or many GPUs and some FPGAs as well. Regarding processing in memory or pure processing in memory, we can talk about 2D PNM, where memory and computation are both inside the same chip, fabricated with memory process. That's the case of HB-PNM, and that's also the case of SK Hynix AIM. And probably in this part, we can also have SIMDRAM or HB-PNM, even though HB-PNM is more or less in between of 2D PNM and 3D TSV PNM, because SIMDRAM is built with HBM2 memory. However, instead of placing the computation in a separate layer, in the logic layer of the buffer layer of HBM2 memory, the processing elements are in the memory layers themselves. More difficult to classify here is AX-DIMM, because AX-DIMM, even though it's processing near memory, in reality, we have memory and computation in separate chips, but they are not connected through a, let's say, memory bus, a traditional off-chip link, but the FPGA is on top of the DIMM itself. And the last of these cases, the last of these processing near memory architectures is the one that we are going to talk about today, is this 3D HB-PNM that is based on hybrid bonding, as we will see. The last group in this classification is called 2D computing memory is what in this course we call processing using memory, and here we have non-volatile memory technologies, but also other approaches to processing using memory, such as processing using DRAM. We will talk later in this course about SIMDRAM as one recent proposal for processing using DRAM. This classification is pretty much similar to the classification that we have in the book chapter, where we distinguish between two main approaches to processing in memory: processing using memory and processing near memory. As you can see in this table, we list several example enabling technologies, most of which are in the previous slide, but also some other ones like logic near the caches or logic near or in storage devices. And here you can find a link to this PIM book chapter. So now let's talk about HB-PNM. It's a 3D stack, logic die, and DRAM die vertically bonded with by hybrid bonding. As you can see in the figure, there is this DRAM die on top of a logic die. DRAM die is composed by these DRAM cores of 1 gigabit, and the logic die has different a couple of two main processing elements that are the neural engine, called the neural engine, and the match engine. In this nice cross-section illustration, you can identify the chip package, the heatsink, the thermal adhesive, and the DRAM die and the logic die connected with the hybrid bonding on top of the substrate. In the logic die, there are these so-called match engine and neural engine that are for matching and ranking in a recommendation system. We are going to talk briefly about this sequence of steps in the recommendation system, but in principle, most of the computation of the, as we will see, most of the computation of the coarse grain matching is done in the match engine, while most of the computation in the fine grain ranking step is done in the neural engine, as we will discuss. We will give in the previous lecture an introduction to recommendation systems. Here, I can refer you to that lecture for more details. Here, we are just describing what comes from the paper from Alibaba. They are considering a recommendation system where there is a first stage for feature generation. This applies mostly to images, is the example that they are considering in this feature generation step. There are three steps. Three steps: classification, object detection, and feature extraction. And they identify this part as mostly compute bound, and that's why this is a good fit for GPUs. In the second part, called matching and ranking, it has two different steps. The first one is coarse grain matching, the second one is fine grain matching, and what they observe is that these computations are mostly memory bound. Most of the latency and the energy, as you can see on the slide, is spent on the access to data. That's why this is not such a good fit for GPU, and these operations are typically run on CPU. These are the two parts of the computation of the recommendation system that are going to be offloaded to the HB-PNM system that this paper proposes. Regarding matching and ranking, as I said, first of all, it happens this coarse grain matching. In this case, the input query is compared to binary feature vectors of 512 dimensions. There is a distance calculation done, and depending on the distance, the top 1,000 items are selected from 40,000 items. Next, the 1,000 best matches are sent to the fine grain ranking. In this case, features of 8 bits by 1024 dimensions are used, and they are fed into the 3-layer MLP for similarity prediction. Out of this similarity prediction, the top 100 ranking results are selected out of the original 1,000 items. As you can see, these different steps are executed either on the match engine or the neural engine. For example, this part here, these two on the match engine, these similarity prediction in the neural engine that runs the MLP, and again the top 100 ranking again in the match engine. And as a result, there will be the query results that the recommendation system produces. So let's talk very briefly about this technology, 3D logic to DRAM hybrid bonding, and how these chips are fabricated. Basically, this consists of fabricating the DRAM wafer and the logic wafer separately. One of them is rotated and face down, and they are glued together with this hybrid bonding process. The good thing of this hybrid bonding process is that it allows very fine-grained communication between both layers. It allows a very reduced pitch between these vertical interconnects, and this way a very high bandwidth between the DRAM die and the logic die. In the longer version of this lecture, you can find a little bit more details that come from the paper, and also a comparison of the pitch to HBM memory technologies. As you will see, this is one of the reasons why the hybrid bonding technology can provide very high bandwidth between the DRAM die and the logic die. Now let's talk about the HB-PNM architecture itself. As you already know, it's composed by a DRAM die and a logic die. Inside, and in the DRAM die, this one is composed by 6x6 DRAM cores of 1 gigabit, and each of them has 8 banks, and each of the banks has an I/O of 128 bits. Inside each of the banks of 128 megabits, there are 8 megabit on-chip ECC. Here you can see a closer view of each of these DRAM cores. In particular, you can see here 4 of these DRAM cores, each of them with their 828 megabit DRAM banks. And here at the bottom, the logic die with the neural engine and the match engine. Observe that on this side, and in this side as well of the engines, we can find the memory controller and the physical interface. These ones need to overlap exactly with the place where the corresponding physical interface is in the DRAM die. And this constraint, this design constraint, is imposed by the hybrid bonding process, because obviously you need to have the memory controller in the place where, and the vertical connections in the place where they can access the DRAM banks. So now, if we take a look at the logic die, we see that it's composed by a match engine and a neural engine for matching and ranking in a recommendation system. And here you can see a closer view of both with the match engine, the neural engine here, and both of them have access through these dual mode interfaces and memory controller to the different DRAM blocks of size 1 gigabit. They have direct access to, so each, these engines have direct access to their counterpart DRAM blocks, those that they have on top, and they also have access to other DRAM blocks via the on-chip bus. The dual mode interface is called that way because it has 2 modes. One mode is all 8 banks access in lockstep for full bandwidth. The other one is a single channel access, 1 out of 8 banks. And here you can see a nicer picture of the dual mode interface, where you can identify controller and then some input and output, FIFO queues, command queues, etc. For a more detailed description of this dual mode interface, I refer you to the longer version of this lecture. Now let's take a look at the match engine. This one is responsible for coarse grain matching. And as you can see, it has 2 main units that are here colored in orange, the distance calculator and the max heap top K engine. The distance calculator obtains the similarity between the input query and the feature vectors, and it computes Hamming distance of two 512-bit vectors. So we have one vector for data, one vector for query data, and here we compute the bitwise Hamming distance, adding these two partial counts, and that resulting in a distance. This distance is compared to the root of the max heap in order to see if the distance, this particular data goes through or it's filtered out. Yeah, that's basically what this unit here does. So now in the max heap hardware block, it also contains a data structure for 1000 nodes, and there is where the 1000 shorted distances are going to be stored. And it's not only the distance, but also the address of the specific feature. And this is more or less how it works. There is one new distance that may arrive every 2 cycles, and in this sort of tree, what is being done is that every input that is received is compared to the left child, and if it's less than the left child, it's swapped, and if not, it's swapped with the right child. And here in this nice figure here, you can see more or less the process, how a new input is coming every 2 cycles, and as soon as the new input comes, is compared to the left child. If it's less than the left child, these two are swapped, and they keep comparing, and these comparisons continue happening for the previous input, even when the current input is received. Now, let's talk briefly about the neural engine. This one is responsible for similarity prediction for fine-grained ranking. And as you see, it has 2 main units colored in orange, the VPU and the GEM. The VPU, or vector processing unit, has 2 main components. The first one is the activations based on lookup tables. Is this activation unit based on lookup tables? It has support for YELU and for exponentiation, and with that, it's possible to calculate activation functions. And the second part is a transpose unit that is composed by these 2 2-dimensional register files. These are of size 16 by 16 and operate in a ping-pong fashion. As you can see, and the writes to this transpose unit are done in a row-based manner, and the reads are done in a column-based manner. And this is the way of performing the transposition operation. Next, regarding the GEM unit, this is a systolic array. Basically, it's a 32 by 32 fully pipelined systolic array that receives int8 operands and accumulates partial sums in an int32 accumulator. And this is a comparison table that the paper includes. It's here for your own reference. As you can see, there is a column for specific to the computing memory proposal for HB-PNM, for an A100 GPU, for HB-PNM or SIMDRAM, and for this work. I just leave it here for your own reference. If you want to learn more about this HB-PNM architecture, I can refer you to this previous lecture that is a little bit longer with more details about this architecture, and I hope that you will enjoy it as well. This has been the last one of the real-world PIM architectures that we have covered in this course, 5 in total, as you can see on this slide. The first one was the HB-PIM architecture based on DDR4 D modules. The second one based on HBM2 memories in DRAM or HB-PIM from Samsung. The third one was SK Hynix AIM based on GDDR6 memory, and the next one Samsung AX-DIMM, a DIMM-based PIM solution. Among all these different, this variety of current real PIM architectures, there are certain differences for sure, because some of them are near bank. That's the case of HB-PNM, DRAM, AIM, or HB-PNM, and while others, AX-DIMM in this case, is more like near chip or near rank. Some of them have general purpose processors. That's the case of HB-PNM. Others have special function units or SIMD units in SIMDRAM or in AIM, in HB-PNM. As you have just seen, they are also more specialized execution units, and they support different execution paradigms, fine-grained multi-threading in the case of HB-PNM, SIMD, or systolic array that we have just seen for in HB-PNM. And they support also different types of operations and data type, HB-PNM or HB-PNM natively integer, while the floating point is supported by FINDRAM and also by AIM as well, and also by AXTeam. It all depends on what you program in the FPGA. And they have different memory technologies, DDR4 or LPDDR4 or HBM2 or GDDR6. But they also have some common characteristics. First of all, there is a host processor in these systems, a CPU or a GPU, that has access to a standard main memory and PIM-enabled memory. This PIM-enabled memory contains multiple PIM processing elements or Ps with high bandwidth and low latency memory access. These PIM-Ps run only at a few hundred megahertz and have a small number of registers and a small or no cache or scratch pad. And these PIM-Ps may need to communicate via the host processor. This is more or less how one state-of-the-art PIM or PNM system might look like. As you can see, there is a standard main memory, the host processor, and the PIM-enabled memory that is composed by memory arrays, either ranks or banks, and then some sort of PIM processing elements that might be SIMD units or general purpose cores or even more specialized engines as the ones that we have seen in today's lecture. So this is all for today. We will continue next week with another lecturing on processing in memory course. We will continue talking in this course about processing using memory architectures and prototypes, case studies, such as, for example, SVMV on the HB-PNM PIM architecture, and a few more. And at the end, we will also have some lecture about enabling the adoption of processing in memory. So this is all for today. I hope that you found it interesting. Please don't hesitate to contact me if you have any questions about this lecture or about the course, and I hope to see you in the next one.